let's crack on. Well, firstly, it's just great to actually be here in person. We've got a fantastically large auditorium for the quite a small number of people, but it still adds a certain gravitas, hopefully, to the settings. But it's been quite nice, just the experience of actually traveling to do something rather than doing it online, even if it's slightly less convenient. Ooh, I'm so sorry, but my clicker isn't working anymore. Okay, cool. So just see a quick look over the agenda. Firstly, you can have me for 5 or 10 minutes giving a very high-level project introduction. I'll just go a little bit through what Resourcecode is about. Then we'll have Nicola talking through the Marine Data Toolbox, and Mikhail talking through the database, which has been produced by the project. And then finally, we sort of get into the real meat of the day, which is where we go for the toolbox itself and actually do a live demonstration. So Nicola will actually work us through the toolbox and give us a live demonstration of how to use it. And finally, we'll have plenty of time at the end for Q&As and to try and tease a bit more information out of us and everyone who's online too. So the project in general, an overview. So Resourcecode, we've been going for about 3 years. We're funded by the Ocean Energy ERANET co-fund. And the high level aim is to create a combination of a HINDCAST data set and a toolbox in which to use it to provide some easy, free, validated, meaningful data for developers and consultants to use in marine energy, in wave energy. The main users will likely be within the developer community, but not exclusively at all. You can see people within consultancy and within academia getting a lot out of what we're doing. The consortium themselves, so this is us, although without me, it's a long time before I start this project, way back when we were allowed to all meet in the same place. We're a group of academics, academic specialists, technical experts, and led by the European Marine Energy Centre, who I work for, who are leading on the project. And it's a very talented, committed, and dedicated bunch of people who sadly I've been able to spend basically no time with whatsoever in the last year, thanks to our lockdown. But we've got a very broad group of skills and a good group of people working on the project. So into the real meat of what we're delivering, so what the project is actually set out to do and what we've done. So first and foremost, we've delivered a detailed HINDCAST data set, which has got 27 years worth of real wave data, which is incredibly valuable, obviously, in its own regards, but also when linked up with our second deliverable, which is the easy-to-use toolbox, provides a fantastic platform for quick and easy calculations and for allowing experts and specialists to quickly and easily work within this field. As I said, the principal users will be in the developer community, but also in consultancy and in academia. And some real-world examples of where we're trying to create value is in a potentially developer who's looking for a site will be quickly and easily able to do some resource calculations of potential sites and then use that to inform further, more detailed work. Also, it would be very valuable for developers who already have a site and want to do some verification work and some initial high-level design, and again, guiding the actual detailed design itself. And it would be fantastic for actually increasing the general data and knowledge within the industry and then allowing us to share that amongst institutions. We're aiming to do a few things for the industry, and I guess they're relatively self-explanatory. But firstly, by being open sourced, it creates and reduces physical barriers to get the data. It means that more people can actually access trusted and reliable data and then use that to actually come into the industry. By being free, it reduces cost and particularly reduces one of the principal barriers to entry, allowing, again, more people to invest in other areas of their work and of development. Through the reliability and the quality of data, it creates a lot of assurance, which is both fantastic for reducing risk, particularly around environmental conditions, but also around attracting investment into the industry. It's absolutely crucial for that. And finally, within the knowledge area, it brings together academic experts, industry experts and research and test centres to actually share and better utilise each other's data and expertise. And that's probably a reflection of how we've worked within the consortium so far. So in terms of where we are at the moment, the data set and the toolbox are nearing completion. We're at the point where we're actually going to be talking you through them today. But in terms of next steps, as we move into the end of the year, we're moving into the trial phase. And we're very keen to connect with people who maybe are in a position where they'd like to come and do a bit more of a detailed test and trial, both in our data sets and our toolbox. And we'd be very keen to hear from any of you. And please feel free to reach out to us either through me after the presentation or to the website below. And so it's a very important and valuable part of what we're going to do going forward. So please do reach out. And I think that's about it in terms of the very high-level overview. Up next, we've got Nicola, who's going to talk through the HINDCAST dataset. So over to you, Nicola.
Thank you, Matt, for the complete introduction about the project. So, yes, I'm going to talk about the marine data toolbox that has been developed within the project. So if we can go to the next slide, Matt. Yeah, so we'll present the objectives, the web portal for the data access, and then the Python toolbox itself. Next one, please. Yeah, so in more details, the objective of the toolbox is twofold. In fact, the first of all is to provide a way to access the dataset easily and as easily as possible through a dedicated web portal in order to allow to extract very quickly time series at a given location, for example, and to obtain also easily simple statistics or summary statistics about the location of interest, and based on the data produced within the HINDCAST task. Michael, who is talking right after me, will present in more detail what has been constructed, how the data has been constructed. So for now, we'll assume that the data is well constructed, and we will explain how we managed to extract data and what are the tools that are provided. So as I said before, the idea was to allow for fast extraction of the data through a dedicated time series, which is called Cassandra, which allows time series oriented storage, which means that the data is stored within a time series format. And the idea is to also to provide developers with a support tool for an online analysis, which means that the developers are provided with global statistics at a location they want, and also provide assessment of the resource, and also extreme value modeling, which I will talk into more details in the following part. There's also a producible assessment, which is will be described next. And last but not least, it is there is a module for operation and maintenance. We can go to the next slide, Matt. Thanks. So the idea is that the data can be accessed by several manners. So maybe the old one, or the one that's been the reference one, is accessing through netcdf files via FTP. But as well, Mika said, this data is very large. It's about 50 terabytes of data that is stored in 13 gigabytes files for each month. So the larger number of files and the big files. So it may be not very convenient to access, or it can be very difficult for people who are not very keen on manipulating netcdf files to download and process this data. So the idea is that this data has been ingested once into a dedicated database, which is called Cassandra, which is an open source software that allows to store this data in a time series oriented manner. And the result is that we can directly call this Cassandra database and obtain a time series of parameters at a given node. And the client will not be able to access directly the Cassandra database, but it will be available to two different manners. So the first one is a web portal that I will show just next. It is a very high-level tool, which means that it's just a click and play. Sorry?
I think you just got a bit of feedback there.
Okay, no problem. So the user will can use a web portal, but it will be, of course, very restrictive because, well, anything cannot be available through the web portal. Very long computations cannot be done through the web portal. And so we also developed an analysis toolbox that will allow us to directly call the Cassandra database through your the way you want. So for example, if you're keen on Jupyter notebooks, then you can just use the Jupyter notebooks to use this Python toolbox, or the command line interface for Python, or anything you want. And this toolbox will be available on PyPy as soon as the project is nearly finished. It's not the case yet, but it is nearly available. And we have some tools that we'll present just next. If you can go to the next slide, Matt. Thanks. So I said before, there's a dedicated website that is resourcecode.fr that will present project presentations and news. It also provides a dynamical interface to retrieve the data. I will show during the demonstration part how it is constructed and how it can be used. And you have a small example on the right here, where you see there is a map. There is the points in blue. You can choose, the user can choose any point and obtain a summary statistics and obtain the time series for some of the available variables. And also we'll provide some use case said here, as shown here. There's a statistical summaries. You can think also about extreme value analysis, environmental controls, weather windows, and something like that. We'll go into more details next. And the Python toolbox will provide a more advanced tool to access the data with some utility function and the tools that I said before. So if you go into the next slide, Matt, I will start to explain what is the functionalities of the toolbox. So for example, you can select nodes from the coordinates. You can obtain the closest node from the location you're interested in. You have access to the full computational grid and also the coastlines that are included into the toolbox. It's very easy to have some maps and to something like that. You have the full list of nodes where you have the full 2D spectrum. You also have the variables, the names, the units in a unique place. You don't have to access the nested files. And there is also a set of utility functions that may be convenient. So for example, you can convert from the zonal meridional component to the magnitude interaction, and you don't have to struggle to see what definitions used and so on. There's also tools to compute the C-state parameters for the 1D and 2D spectrum. So everything is unified. There's also the fit of the transfer spectrum from HS and TP. So again, it's to be sure that the computation made with the toolbox are unified and will always get to the same results. So if you go to the next slide, Matt, you have I have an example here of extreme value modeling. So the extreme value modeling that has been developed within this toolbox or implemented within this toolbox is adapted from a paper that has been recently recently published 2 years ago. Well, it's a way to model multivariate extremes and to obtain the dependent structure for multivariate models. So I will not go into details here, but the idea is to is to model the dependence and to construct what is called environmental contours, which are hypersphere, where the written level is located in a multivariate context. So in 1D, you look at the written level, and in when you have multivariate data, you look at the environmental contour. So next slide, please, Matt. Here, we also developed a methodology to estimate what could be produced by a wave energy converter. So included in the toolbox, we have a device, which is a generic wave bob that has been modeled and using some assumptions. So for example, linear flow theory, linear damping, infinite water depths. We're able to compute what could be produced and how the power takeoff could be optimized on the time series of the HINDCAST database. So if you go to the next slide, Matt. Here there is an example of what can be done. So for example, on an hourly basis, you take the spectrum, the Resourcecode spectrum as input in your wake model. You undergo some PTU optimization, and then you have an estimation of the prediction that at each time step. So there is an optimization behind, so you can have multiple curves, and you can estimate the prediction at each time step. So if you go to the next slide, Matt. So here there is also an adaptation to take into account non-linearities as the power takeoff, as the power extracted will be decreased when the steepness is too high. So if you want some more details about this estimation of the producible, you can attend to Gregory Payne talks on Tuesday. Will be Tuesday morning in the wave resource characterization session, the same as where Mikael will present to more details the HINDCAST database. So if you go to the next slide, Matt, you have an.
Sorry, there you go.
No problem. You have an example here of the time series of HS, time series of TP, and also a mean power estimate that can be extracted. And then last, the power takeoff value for 1 year, it's 1 month of data. And the idea is that this can be computed on the fly from the time series of HSTP or from the spectrum in very quick manner. So if you go to the next slide, Matt. The last function that I want to describe is the weather window. So here for a given location, we want to compute the weather window and the waiting time for for any operation, given some constraint. So the first approach is to use the model-based approach, which is based on a methodology developed during the EKIMAR project. So you fit, the idea is to fit 2 or 3 parameters variable distribution to the HS to assume some shapes of the storms. And then we can derive analytic formulas for the weather windows, waiting time, etc. So we'll show some results of this approach. And this approach only allows to have constraint on HS. So these will also provide empirical estimates of weather window and waiting time using empirical estimates. So you take your time series and you compute the time where you have you're below your constraint and the waiting time for you to have to obtain the constraints. So if you go to the next slide, Matt, you have I provide some example of I will show during this demo. So you can provide probability of occurrence, mean window length here in the bottom part, and also the monthly evolution of the number of events. So you define your constraint the length of your window, and also your constraint you have in the HIS, and you can compute the number, the mean or the expected number of events and the expected time or expected waiting. So that's it for the Python toolbox. Go to the next slide, Matt. University of Edinburgh also developed a standalone validation toolbox that will be provided within the project, which allows to quickly and very easily validate or compare in situ data to the Resourcecode laboratory model. So you can go to the next slide, Matt. So the idea is that the scripts developed by Udin allows for data processing to generate batch jobs to validate and to retrieve quickly the data from the model and to compare or to provide summary statistics or monthly statistics to compare the in situ data to the modeled data. So that's all for the toolbox, the presentation, for the very brief presentation of the toolbox. So
Thank you.
I think the next one is Mikael who presents.
It is. Thank you very much, Nicola. That was fantastic. And we really look forward to actually being walked through the toolbox shortly. Just before we go on to Mikael, and I think a couple of people have done it already, please feel free if you're online to drop questions you'd like answering within the question function on Zoom. Someone will either try and answer them straight away, which I think is what's happened so far, or we'll pick them up at the end and we do the general Q&A along with ones from the room. So please feel free to start putting stuff out there as and when it comes up. But now on to Mikael, who is going to talk through the actual HINDCAST dataset itself. Over to you.
Hi, so yeah, I'm Mikael Asensi, working at Ifromer, and so now I'm going to detail you the HINDCAST database we have produced within this project. So Matt, if you can go on the next one. So this C-States HINDCAST covers the European shelf, as you can see on the figure here. And so it goes from Gibraltar to the south up to the Faroe Islands in the north. And it goes from 1994 up to 2020. And then the idea will be to maintain this HINDCAST by doing yearly updates to get the latest years done also. And next slide, thanks. And so to create the grid for this HINDCAST, so we've used the bathymetry dataset from the EMONNet 2016 and the homonym bathymetry files. So they have resolution about 200 meters and 100 meters. And if you look at the map on the right, you can see the merged product of those two bathymetry datasets on the domain. And here we just filter the color map between 0 and 100 meter depths just to highlight the high resolution of the bathymetry details. And so for the coastline contour, we've used the polygon provided by the OpenStreetMap. And to get more realistic bottom friction parameterization, we have defined a grain size classification based on the sediment map provided by EMONNet and SHOM. And so that the figure below, so you have the map of the grain size classification. And so you can see that it can change a lot depending on the area in the domain. They have a strong impact. And next slide. And so to force the model, so we have used current and water levels. And so since we were not able to find any model output covering the whole domain and the whole period of the HINDCAST, we've used Tidal atlases. So from the Ifromer Tidal Atlas and the FEST 2014. And if you look on the map on the right, you can see the different domain of the Tidal atlases with resolution going from 250 meters on the coastal area, 700 meters on the on the French area and up to 2 kilometers on the Northeast Atlantic. And to cover, and so that's for the ephemeral tidal atlas. And to cover the south of Portugal, which was not covered, we've used the FES 2014 atlas, which is a 450-meter resolution. And once we've used those tidal atlases, we've recomputed the tidal currents and water level based on the tidal components. And so we have interpolated them on each mesh node at a 30-minute time step. And so you can see an example on the map below of the M2 amplitude. And next slide.
Sorry.
Thanks. And so to run the wave model, we've used the wind from the ERA 5 reanalysis, so which is a quarter-degree resolution and an hourly time step. And we have applied a bias correction for the extreme wind to get more realistic results in the wave model compared to altimeter and buoys data. And the wave model we've used is a spectral wave model, Wave 3. It's a latest version 708. With a new brand parameterization we have produced during the project, and all the details are in the publication done by ALDE et al. 2021. And about the spectral discretization, so here we've used 36 directions and 36 frequencies, aiming to be able to resolve the wave period between 1 second and 29 seconds. And about the spatial resolution, so as you can see on the figure below, the mesh is based on triangles with size varying between 200 meters and 10 kilometers, depending on depth gradient and the coastline complexity. And the complete mesh has more than 330,000 nodes. So that's a lot, but that's needed to get really high resolution. And then at the boundaries of the domain, it was forced by directional spectra from a global model at a half-degree resolution, using the same wind and the same parameterization as this one. And next slide, Matt. Thank you. Oh. Yeah, thanks. And so, okay, I can see the. And so for the model output, so here we are outputting up to 39 parameters to fully describe the sea states. And so it includes all the classical one, like the significant wave height, peak period, the energy fluxes, and many more. And but we also provide the directional partitioning, so all the parameters for the wind, sea, and the different swell partitions. And also all the forcing fields like the wind, water levels, and current, and also the depth from the bathymetry. And so you can see an example here on the different time series. So it's an extraction at a given node in the mesh. And so you can see the significant wave height, the different wave periods, and the mean and peak directions. And we also output the frequency and the directional spectra. So the frequency spectra, which is a 1D frequency, is a 1D spectra, is outputted at each grid node at an hourly time step. And the 2D spectra, so in frequency and direction, are outputted at more than 24,000 points at also an hourly time step. And so you can see on the map on the right the location of all the directional spectra, so which cover mainly all the shallow water and intermediate waters, and also many points of interest for the renewable energy test sites, and also all the buoys from the CMEMS Institute Act network for validation purposes. And next slide, Matt. Thanks. And so then for the validation of this HINDCAST database, we have compared the model output against buoys data provided by the CMEMS Institute Act network. And so this database is publicly available. So you can go on the CMAPS website, or it should be also available through the Resourcecode toolbox in the validation datasets. And so here we have computed statistics against different wave parameters. So here's the significant wave height, the peak period, the mean direction, and the spreading. And so you can see on the table the different values for the statistics, which are really good for almost all the parameters, maybe except for the spreading, which has lower score. But in terms of correlation, yeah, we have really high scores, and for the normalized mean bias, we are really close to 0. And for the normalized root mean square error, we are around 20% error. And since all those parameters are not available for all the buoys, you have on the table below the number of buoys providing the different parameters and the number of samples. So you can have an idea here of the amount of data used. And so here it's for the whole period covering this HINDCAST. And you have an example on the map on the left, which represents the significant wave height at the buoy locations. And here it's the root mean square, which is represented. And so you can see that the error is varying between 10 centimeters and 60 centimeters in average on the whole period. And except some buoys with larger error, in average, we have really good scores. So that's pretty good news. And next slide. And so we also perform spectral validation against different buoys provided by project partners and different and also different oceanographic institutes. So those data have restricted access, so don't think they won't be available for public, but you can still have the results of all the validation for each year. So here I'm showing the validation for the year 2013. And so you can see the different location on the map here. And on the side panels, you can see the annual energy per frequencies. And so in dark line, you have the buoy measurement, and in blue, you have the model output. And so you can see that it's fitting really well, except maybe for some areas in very shallow water and sheltered areas. And those areas with lower scores are circled in red. But in average, looking at each year, we can see that the scores are really good. And next slide, Matt. And the last validation we have performed was about remote sensing comparison. So here we have used the CCI Seastate altimeter database version 1. And the version 2 is just released 1 or 2 weeks ago. And also this database is publicly available. So you can go on the CCI website to download all this altimeter database. And it should be also available through the Marine Data Toolbox with already performed co-localization against model output. And so here what we have performed, so we have done matchup between the model output along each altimeter tracks. And looking at the overall statistics per altimeter on the table on the right, you can see for each line the scores for each altimeter. And if we focus on the last line, circled in blue, so it's a merged product. So it means that's all the altimeter data and model matchups gathered in one merged product. And there is an advantage in that, is that it's covering the whole time series up to 2018. And so you can see for the bias that it's really close to 0 in average. And for the error, we are about 30 centimeters error in average, which represent 10% error normalized. And if we look at the time series to have an idea of the scores for each year, for each altimeter, so you can see the scatter index, the normalized root mean square, and the normalized bias here below. And so each color represents an altimeter. And if we focus only on the dark line, we can see that it's pretty steady over the years, and with a trend to have even better scores on the latest years. But it's more related to the accuracy of the new altimeters algorithm and instrumentation. And once we have the matchup between the model along the altimeter tracks, we have performed averaging of all those data on a regular grid at a 1/8 degree resolution. And so that's what is shown on the map on the left. And so you can see that the normalized bias on the figure A, and the normalized bias is varying here between -5 and +5%, with a trend to have a slightly positive bias in the Atlantic Ocean and a slightly negative bias in the North Sea. And those differences can be due to the wind forcing, but also to the model parameterization, or either to the altimeter data processing. And on the figure B, you can see the normalized root mean square error, which is about 10% with a slight increase of the error in the North Sea and closer to the coast. And here for the processing of those data, we have removed all the altimeter data about less than 1 meter because they are really noisy data. And we have also removed all the data at less than 50 kilometers to the coast due to the noise also in the altimetric data. And on the figure C, you can see the amount of matchups, which varies due to the altimeter tracks. And so it varies between 50 and more than 200 measurements in average. And on the last figure, figure D, you have the correlation coefficient, and you can see that we have a really high correlation on the whole domain with a really homogeneous values. And so all this data set is already performed and almost available through the FTP access, as Nicolas said. And then in the second step, we will also include all the validation database, so the altimeter and the buoys from the CMEMS Institute. And that's all for me. And so I will let now Nicolas talk you about how to use all those data in a real demo right now.
Fantastic, Mikhail. Really, really good. And just as always, when I hear you speak about that stuff, I'm just amazed about the amount of work that's gone into both collecting that data, but also particularly validating it. And we don't throw around words like validate unless we mean it. And it's great to see the effort that's gone in there. So finally, it's over to Nicolas, who is going to share his screen and walk us through the actual toolbox itself. So Nicolas, over to you.
Yeah, just while we change the screen and we do everything we need, feel free if you have some question to ask to Mikhail about the HINDCAST or to me about the toolbox. Matt, I cannot share my screen. I think that you have to stop sharing yours.
Okay. Sorry. 1 second. Sorry, could you stop sharing the screen on that, please? Thank you. It's okay. It's being shared from the other side of the room, which isn't quite so easy. Hopefully, you should be able to now.
Okay. Okay. Are you?
We are seeing that come up. Yeah.
Is it okay? You can see it?
Yeah, we can see it. It's not quite full screen, but it's pretty big, so I think it should be okay.
Okay, so here it is the main page of the Resourcecode website on the resourcecode.ifremer.fr. So we have just a presentation of the project. with the objective and so on. So it's everything that Matt already shown already explained. So we will also put in this place the news and the relevant information we can provide to the users. So for example, when the toolbox will be released and things like that, so you can keep it informed on this website or on the Resourcecode.info website. So now we can go in more details to the web portal. So it's look like this. So you have the map, as Michael already shown to you. You can see the locations of the points where the nodes are located. So it's only a subset of the nodes, because here we have a very large number of points, so it's just a small subset. But as you zoom to a specific location, so for example, here, if you want to zoom to the South Brazilian, you can update here and refresh to obtain the grid that corresponds the points that are zoomed into this this area. So you can go into more detail about a specific zone. So here it's only a few statistics for a few variables that has been computed to present here. It's not the whole data; it's just a subset to be able to print it. So we've computed summary statistics for the wave energy flux, for the current speed, for the significant wave height, peak period, wind speed. So we're thinking about including maybe some of the variables, but well, we are thinking about it. So you can choose here the variable you want. So for example, if you're interested in the wave flux energy, you can select it. Then the map will load to show the statistic of this variable at each location. So at each location, you have the summary statistics for the whole time considered. So this is from the beginning, in 1994 to the end. It's up to the last computed time. So for now, we have the minimum value, the standard deviation, the max, and the mean, which is not shown here, but it's computed. So you will be able to select which of the 4 statistics you want to show. So if you want to look at the maximum value of the wave energy flux at a specific location, then you can zoom in, you select your variable, your statistic, and then you look at the location, and you can see the areas that are the most impacted or the most energetic. So it's just an exploratory map, and it changes when you click a specific location. So when you hover on a point, you see the point number, the latitude and longitude of the point. And when you click on it, then you have several use cases that will show up here. So the first one is a very crude experimentary data analysis. So what's going on here is that when you click here, the data is retrieved from the Cassandra database. The time series is retrieved for the whole period. And then you can compute, you can visualize the several variables. So here is a very crude example. When you have significant wave heights, the peak directions, the depth for the time series selected, and you can compute the mean value, standard deviation, and everything is computed on the fly. You can also think about having a time series here, which shows here for 1 month of the time series. And also you can compute the histograms, the reparations is computed on the fly. So the idea will be to to be able to specify a period of time where we want to retrieve the data, and you will be able to retrieve the data from a specific time to a dedicated set to the time you specify. And next, if you don't want, if you already have the point you're interested in, you can here enter the latitude and longitude, the point you want to look at, and it will automatically choose the closest to the location you want to look at. So it is the maps that allows to select, and it's not available yet, but the idea will be to give access to the data. So once the data is extracted in this website, then the data, you will have a button that will allow to download the data, to download any of the pictures, etc. So if you want to zoom at a specific time or to extract the time series for a specific time, you will be able to extract the data and to plot to save the plots, to save the histograms and the computations that are done. And here it's not populated yet, but we will show the tools that will show you just here. You will have the notebooks that corresponds to the demo that I will show you just now. So the first notebook or the first use case that I want to show, it's an exploratory data analysis using this data and the toolbox that is provided. So here I do not show the corresponding code, but it's a Python notebook, and it's provided. It's computed with a very few commands. When you click on the tool tab on the website, you will have access to the whole notebook, and you can look at the code and change it yourself and read it. So just show here that within the toolbox, you have access to the computational grid. You have the node number, the corresponding longitude, latitude, the depth, and the classification that Michael talked about to retrieve the granularity, which means the 4 things that I used. You also you have the same table for the locations where we have the full 2D spectrum data, with the node numbers, the longitude, latitude, the name of the point, corresponding depth, and the granularity. You also have a dedicated method called the get closest point, which allows to get the node closest from the longitude and latitude you specify. We also have into this the toolbox possible use coastline and islands, which allows to very quickly show maps as shown here. So we can extract the node in blue, which is the computational node. In orange, it is a spectral grid. In here, for the sake of the example, I took a specific point next to west to show what we can do with this data. So once you've selected your node, then you just have a simple command, just one-liner to extract the data from the Cassandra database, and you specify your node and the variables you want. So here, for the sake of example, I've retrieved bytes, the FP, the peak frequency, the direction of the peak frequency, the wave energy flux, and the zonal meridional velocity components for the wind. So here, just the tail, the last lines of this data, last rows. So you can see that you've extracted this variable from the database. So it's a one-liner, and it's almost you retrieve the data almost instantaneously. We have also helpers functions that allow us to compute the peak frequency, sorry, and also the wind speed and wind direction from the zonal and meridional velocity components. So you obtain those variables. So you have HS, the components. Here retrieve the mean period T02, FPDP, CGE, the TP, computed wind speed and wind direction. And I provide here just a summary table with the mean values for each variable, standard deviation, mean value, max value, and some quantiles. So here to show you that the whole data is retrieved, I've shown the whole time series here within an interactive plot, which allows to zoom. For example, if you want to zoom at this extreme event, you can specify the location, and then you zoom and see the different variables, how they evolve during time during this event. You can zoom, and for example, you are able to download this plot. I show also what is can be computed very easily. It's the bivariate statistical distribution. So you have the 4 variables: HS, TP, wind speed, and CGE. So you have the histograms here on the diagonal, and a scatter plot representing the data. You can also compute with this box very easily the wind roses. So it's the repetition of the wind's intensity depending on the direction. And finally, the wave rows, where do the waves come from, depending on the intensity. I also show examples of monthly statistics. So for example, here you can compute the monthly histograms of the HS, monthly histograms of the wave energy flux, and also the wave wind roses by month, for example. Here to see the seasonal variation of the wind direction, and also the wave roses, monthly wave roses, where you can describe very easily the statistics of a specific location. The next tool I want to show is about the modeling extreme values. So I will not go into very details about the statistical models that are behind the hood. But here, I just extract the data from a location that is located next to Berlin, in Belle Island, next to the Brittany coast. So here you have the head of the data. The extracted time series here. So I extracted three variables: the significant wave height, the wind speed, and the current speed. And I provide some examples of what can be obtained with the toolbox. You can compute the written values here using a POC model that is fitted to the HS. Just a one-liner to obtain these plots. You have the probability density plot, the QQ plot. You see if the model is well adapted. And you can compute the written levels associated to different written periods. So if you're interested in the 100-year written level, you can have access to this estimate and the associated confidence intervals. And as explained before, we developed multivariate models to estimate environmental contours. So for example, in this very example, you can look at the environmental contours associated to a given probability of exceedance, meaning that it's a kind of analogous to the written level. You expect your C state to be above, for example, the red curve once every 100 years. So it's equivalent to the 100 written level. So it's and you have your plot here, which is much more easy to visualize. You can zoom in to look, and you can retrieve the data you want. So for example, if you want to estimate the response of your device in a specific point, you can obtain this curves, and the data will be able to to be downloaded. So you can download the corresponding values here of the green curves, the red curves, the blue curves, using a very well-defined methods and reproducible method. And the last tool that I want to show here is the estimation of the weather window. So I took the same point next to Bailey Island. And for the here, I use the methodology described in a Ekimar project. So the first step is to fit a variable distribution. You minimize the distance between your empirical CDF and the variable CDF, and you obtain the parameters. So here, the model is fitted for each month. So you have the 3 parameters variable that is estimated. Here's the blue curve, the fitted curve, and the empirical CDF is the red curve. And once this model is fitted, you can compute several things. So the first one is the mean window length, which represents the mean duration of consecutive time below a given HS value. So you have this value for each month, this curve for each month. So for example, if you're interested in the month of August, then you have the mean window length for a given significant web height. So for example, here, if you want to the HS net to exceed 2 meters, and on average, you have 88 hours below this threshold. The next plot I want to show is the probability of occurrence. So it's a probability to have a weather window corresponding to the statistic you want. So for example, if you are interested, if you want to install something within the month of August, and depending on for example, the vessel you want to use, depending on the operational conditions. So for example, if you're going to operate to up to 3 meters, then you can expect to have a weather window of 100 hours with a given probability. And of course, as the threshold lower, the probability lowers, because having less than 1 meter at this location is less possible than having less than 3 meters. And last but not least, we can show the monthly evolution of these characteristic curves. Here, I think I have to zoom out a little bit. I hope it will be okay for everyone. So here we have 3 curves, depending on the weather window you want and the constraint of HS. So for example, if you have 24 hours to operate and you cannot exceed the 2 meters the HS, then you can see the number of time such kind of event do occur in the time series, depending on assuming that the model is right, and depending on the month. So of course, during the summer months is more likely to have such events. And you can also look at the access time, the mean number of time, the mean length of the window. And the last plot is the waiting time. It is the time you have to wait before observing such an event. So of course, in the summer month, again, it's lower, meaning that you have to wait less time before having such windows. So that's it for the examples. Once the toolbox will be released, we'll also have a documentation page that will be available. So now, once the package will be released, this website that will be also shown on the Resourcecode website will be available. So you will have details to how to install the library, example of way to query the data with the example of use and example for the function term. We also have examples of the helpers function. So for example, the function to get the closest point, what variables are available to get something like that. You also have some example of what is available for the weather window. So again, we have the references to the eCamera project, and then the distribution of the functions that I used to construct the notebooks that I've shown. So for now, it's I think it's all for me. So I hope it was clear. I don't know if you have any question, if you want me to go into more details, or if you want questions to other partners of the project. Feel free to ask.
Thank you very much, Nicolas. Just having a quick look through the Q&A, and I know that people have been answering them as we go along, but we do currently have one open, from Hélène Pinault. Have you made some comparisons between Resourcecode and Omer? Do you recommend to switch from Omer to Resourcecode at all locations when fully available? I don't know if there's anyone on the panel who'd like to try and take that one.
So yeah, so I can reply to this question, and so yes, Hélène, we've performed some comparison between the previous project Omer, in which we performed the same kind of HINDCAST, and yeah, so the Resourcecode is slightly better and is more up to date, in the meaning that we have done a new parameterization, and we've also used a different wind forcing. So in the previous project Omer, the model was forced by the CFSR wind reanalysis, and here that's the ERA 5 wind reanalysis. And also in terms of parameterization, it's slightly better, yeah. And so we've performed different comparisons between Resourcecode output, Omer output, and some buoys output. And usually it's better to use Resourcecode. So if you can switch on Resourcecode once it will be available, that's better. And then if you have some questions, you can still send me an email or to have more details. And I have almost finished the documentation also for the database. So it will be also, the documentation will be also available with the database, and documentation also for the model validation against in situ buoys will be also available with that. So you will see in these documentations the scores for the model.
Fantastic, thank you. Do we have any questions at all from the room that you'd like me to put through? Yeah.
What I think very interesting was the option that you can directly from the interface see how much power you absorb with this wave energy converter. I'm now interested, is there any option to include a known or an easy interface to include a known model of wave energy converter, or to get this data out so that it can be run with simulation of wave energy converter?
So I will let you answer that again. Ask that again if you may with the speaker, just because otherwise I might struggle to get all that back. Is that working?
Yeah, thanks very much for this question. So I'll repeat it for the merit of the online audience. So the question, if I understood well, was whether it's possible for user to use their own device model, right? Yeah. So yeah, the idea is that it's possible. So what we provide in the toolbox as it stands at the moment is like a case study with a set of efficiency curve or capture width curve, whatever you want to call them. But the idea is that a user will be able to create their own capture width curves, and using them and using the resource data from Resourcecode, calculate energy production estimate, or the kind of graphs you've seen. But in order to do that, this won't be you won't be able to do that online. You'll need to do that on your computer using Python. So, but connected to the Cassandra database. That's.
You would have to dive into the source code and
No, well, what we try to do is to make it quite simple and also quite well defined how you define the performance of your device. So this will be, in order for it to work in a robust manner, the way you will need to define those performance will be quite well parameterized. So basically, what you will need to provide is capture with curves as for different values of your damping. But so does that answer your question? Yeah. Okay, thanks.
Thank you. Thank you, Gregory. Gregory's, I'm sure everyone will realize, is part of our consortium on Resourcecode. So thanks very much for that. Are there any outstanding questions online that have been nothing in there at the moment? So in that case, are there any further questions in the room at all, which we'll to address? Otherwise, there's a couple I noticed which have already been answered. It might be worth reading out for the sake of. Not in my chat, no. All I have is the just a request to turn on cameras. Okay. Okay. In that case, let me go through a couple which I thought were quite probably quite useful things to share, which came through the Q&A function, which have already been answered. So actually, Javier asked, is there a help function in order to fully understand the acronyms and how to get the most out of the program? The answer to that from Kyle, yes, there are helpers, which is actually what Nikolai was showing near the end of his presentation. And the documentation as well will give a lot of information for how to use the toolbox. So there will be an element of a sort of a help function within it to help people get the most out of the toolbox. Have another question from Matthew Topper. Can you apply the Python tools to other data sets? Mikhail, yes, you can include your own model output or in situ data as well. So that addresses that point. Jean asks about data interoperability and taxonomy. Is it possible to extract all these result files in order to use them in a standard GIS or as a QGIS? What would be the pitfalls to avoid? Mikhail, I don't think this would be possible to incorporate the model output directly in QGIS since it's triangle based. From what I know, it is possible to display the model output by using NCWMS2 web service. If you want to visualize the data on QGIS, you might need to convert the data onto a regular grid, which would be another solution. So there'd be some interoperability there. And Javier asks, do you have a way to compare the wave potential with wind or solar for a particular point, particularly in the availability of the resource? Nicola answered, we do not provide estimates of wind or solar energy. However, the ERAS wind data used as forcing wind is available, so one can process the data to estimate available energy. And I think, finally, hello, thank you for introducing Walker. Will the user bathymetry data be available? For instance, will the user get the water depth and extracting time series? Mikhail answers, yes, it will be available. And I think that's all the questions I've got so far. Has anyone got anything else they'd like to ask? A little bit more time left if needs be. Okay, anything else from online at all? Any of the other panelists want to either add or ask anything before the end of the presentation? Okay, wonderful. Well, I'd just like to say thanks very, very much, particularly to Nicola and Mikhail for presenting, but also for everyone for joining us here today. It's been a fascinating experience for me actually being involved in this project, and it'd be great over the next few months as all of these tools go live and we actually get to see them being picked up and used in real world scenarios. So an exciting few months ahead, and thanks ever so much for joining us today. Okay.
Thank you, everyone. Thank you, Matt, for chairing the session.